Hi, this is Peter with CalcBook, and today we're going to be looking at a timber connection design, specifically looking at a lag screw in withdrawal and looking at what happens when we are in an end grain condition. So just a quick recap, right, of our timber connection design. We are using the National Design Specification, also known as the NDS. And we have two items that we use. We use the NDS spec, and we also use the NDS supplement. So the spec gives us our design procedure, capacity equations, adjustment factors, that sort of thing. Lets us decide, our load direction, whether we're in lateral or withdrawal, and our, type of fastener. So for CalcBook, we focus on the dowel type fasteners. Those are your bolts, lag screws, wood screws, nails and spikes, those sorts of things. The supplement does not get used as much for connection design, but we still may need to reference it for any type of member properties. So this is where you'll find all your information for Douglas fir larch or southern pine, those types of things. You can find all those material properties and reference design values. So we are going to be focusing on our withdrawal loading for lag screws, and so when we're using lag screws, we're using that first equation there, 12.2-1, to find out the nominal withdrawal load for an individual fastener. So let's take a look at our problem statement. Right, we have a connection design here. It appears to be maybe a header connected into some studs there, and maybe we have this as a collector, so we have an axial load in this member. We have Douglas fir larch members. We have a lag screw. We have 3 lag screws there. The lag screw diameter is 3/8 inches, and it has a penetration depth of 2 inches into that header member there. So that orange color, right, that's what we're going to be checking for our withdrawal capacity. We have dry fabrication condition and a dry service condition. We're going to be using ASD loading. And the total axial load due to earthquake is 2,925 pounds. And so that means per bolt, we just divide that by 3 because we have 3 bolts. And that gives us a tension bolt of 975 pounds. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now. So we go and click into our timber design module here, our NDS 2018, and then we'll go ahead and click into our connection design. And we're going to be doing a withdrawal load on a dowel type fastener. So go ahead and click continue. So our dowel type, right, we said was a lag screw. The diameter we said was 3/8. And our penetration depth, right, we essentially have this condition here, and so we really only want the penetration depth into that main member, right, because the side member is not going to be resisting any of that withdrawal. So we just have this main member penetration depth, which we said in the problem statement was 2 inches. Our main member property is going to be Douglas fir larch. And then we need to look at our adjustment factors, right? So we said we did have end grain conditions, so we do need to consider that because it's going into the end of that header beam. We have a dry in-service condition and a dry fabrication condition, so those can stay as is. No temperature condition. And for our time effect factor, actually, we are going to be using ASD, so we need to switch this over first so that we end up with our load duration factor there. And since this is going to be a seismic load only, right, we can use this wind earthquake load and use a 1.6 for that C sub D. So it gives us a little bit extra capacity there because it's an instantaneous load, short load duration. So we'll enter 1.6 there. And then the last thing we need to do is enter in our demand. We are going to be using the ASC 716 load combinations. So we'll go ahead and enter in our seismic load of 975 pounds. It's our nominal load. We'll let the load combinations automatically generate. So we can already see we are about 5% over, so let's take a quick look through the calculation and then we'll update to make sure that our connection works. So we are going to be using 0.7E, that is our ASD load combination for seismic load. We have some preliminary design calculations, right? We have to take off basically the tapered end of the lag screw because that does not provide any resistance, so we take that off based on NDS spec table L2. Our total length of penetration then is just going to be our designated penetration depth of 2 inches, right? Our input depth of 2 inches minus this E value, so a total penetration depth of 1.7 inches, 1.78, excuse me. And then we use that equation 12.2-1 to figure out our nominal withdrawal capacity, about 305 pounds per inch of penetration depth. We go through our adjustment factors, right? We said we had our load duration of 1.6, nothing for moisture content or temperature, and then here we have our end grain factor of 0.75, which comes from NDS spec 12.5.2.1, and our not a toenail condition, so it is just a 1. So our final design connection, right, is our adjustment equation times all of our different adjustment factors, and then multiplied by the penetration. And remember, this is just for one lag screw, right? Because we divided our total load divided by 3, which is the total number of bolts we have. So this is a direct comparison of the load that we entered. And our DCR is just about 5% over, so we can go back and just maybe increase our penetration depth to 2.5 inches, and that gets us into a 0.82 DCR, so that connection works. So that is a lag screw in withdrawal in an end grain condition in CalcBook. We hope you enjoyed the video. If you have questions, please let us know in the comments below, and we'll see you next time.